Hello, thank you all for being here. I hope you enjoyed the pizza. So welcome to the second Apache Airflow meetup. This time hosted by GoDataDriven. So a bit about me. My name is Fokko Driesprong. I work as a data engineer for GoDataDriven. I'm holding a master's degree in distributed systems. And I'm a Apache Airflow committer. So if there are any pending pull requests that you need to get merged, come to me. And beside that, I'm a big enthusiast of open source software in general. So I think it's truly amazing that together, like all the people in the room, and also across the whole globe, we built something beautiful like Airflow. That's something that that I really like about open source software. So one word about GoDataDriven. So GoDataDriven is sponsoring the pizzas and the venue this evening. I hope you like the pizza. It's handpicked by one of an Italian colleague of mine. And so if you're also looking for a job, we're hiring. So if you're like a consultancy, like data engineering or data science, please come talk to me. And we have a new logo, in case you didn't notice. It's the new one. Before we had all these blocks. So about the agenda this evening, first we have a talk about Julian and Bas, about building data lakes using Apache Airflow. It's something that they did together with Knap. Then we have a small break of 50 minutes so you can grab another beer or maybe some leftover pizza. It's called good as well. And then we have Tahir, who's going to introduce us to Cloud Composer, which is managed Airflow on the Google Cloud. And afterwards we can have some more drinks, if you like. That's it. Let's give a warm applause for Bas and Julian.
Check. I think it works. Daar. Oh. Al die apparaten. Yes. Okay. So good to see so many people here today. Today, me and Julian will tell you a bit about building data lakes with Apache Airflow. It's for a project we done at Knap. And we will tell you about what we've done there and our experiences and lessons learned. It's not working. Soms zit deze er los in. Yes. Okay, cool. So I'll do the first part. Tell you some bit of context, what a data lake is, according to us, and some of the software we built there. Julian will go more into the details, testing, lesson learned, and future work. So we've done this project for Knap. Knap is an online-only bank. They do not have physical locations. And their main goals are to enable the customers to make the most of their money, powered through personalized services on the website. For this, they asked us to build a platform to collect the data on, and basically have a kind of playground for modeling purposes and a bit of exploration on data with the idea that they can build new products. So just to sketch a bit of context, our definition of a data lake, basically we define it as a lot of input sources. Just those input sources into some platform, which we call the data lake. On the data lake, it goes through some kind of standard flow, and there's also some output sources, which are generally some external systems, which are used for reporting or analysis. And on this data lake, there are people like analysts and data scientists. We provide them some tools like RStudio and Jupyter Hub, which they can use to analyze and analyze the data and create reports on the data. So a bit more specific, the import sources can be pretty much any kind of format. XML, CSV, JSON, many other types of formats. And the input can come from many different types of sources. Generally, these are REST APIs or SFTP on which people upload data and then we download it onto the data lake. But yeah, it can be pretty much anything from where we fetch the data. Once we fetch the data onto the data lake, it goes through some kind of standard flow. Generally, this is a place, a bucket, which we call ingestion or raw. We process the data, it lands into some kind of processed area where people can work with the data, and then there's generally some kind of export location where we have sets of data ready to export to other external systems. On the output side, generally, in our case, sources are exported to some kind of SFTP server, but people yeah, also accept zip files sent to some email or some other location. So a bit more formal definition. It's a repository of relatively raw format. It's not always possible to really not process the data before putting it on the data lake, but we tend to try to store it as raw as possible. Also, it should be up to date as much as possible. So for analytical purposes, up to date means usually once a day is good enough. But yeah, having it real time is simply not possible in sometimes. And yeah, once a day is good enough. Also, it allows us to build up a historical database. Usually if we take a snapshot of some database or SFTP server, yeah, it's a state of the data at which you get it at that moment in time. But for analytical purposes, it's usually nice to build up some history. Also, we create derived tables from the data that we process. Also, again, for analytical purposes. And the data science lab is kind of a playground for data scientists, data analysts, with tools like RStudio, Jupyter Hub, which they can use to experiment and create reports, create analysis on the data. Last bullet point is very important. They should work on only anonymized data. This is a strong requirement from many people. Before loading it into some usable format, the data should be, the personal information in the data should be hidden because there's no use or there's no goal on working on really personal data. The goal is to build some kind of report or model or new feature, and it's just simply not necessary to work on real raw personal data. So the thing that orchestrates all these processes, and the reason why we're here today, Apache Airflow. For us, this functions as basically the orchestration service to handle all the imports, processing on the data lake, and the exports. From infrastructure perspective, it's actually surprisingly simple. We have basically one instance, is basically one big fat machine running Airflow, Jupyter Hub, and RStudio. For the heavy lifting, heavy processing of data, we use an EMR cluster, basically to run Spark jobs, and we store all the data on S3 buckets. We basically make two divisions in these buckets, unmasked and masked. So is the data anonymized or not anonymized? And unprocessed, processed. Oh, it speaks for itself what that is. And to give you some examples of standard flows which we encounter, here's one. So we read data from Salesforce, a CRM system. We do some select statements on a daily basis on Salesforce, which we then store pretty much unprocessed in an S3 bucket. Next, we apply some transformations on the data. These are typically type conversions. So, for example, the data is loaded as string format, but it can be date times in there. We cast those to date time columns. We anonymize the data, and we create derived tables from the data. Finally, we end up saving the data in a process bucket and make it available to analysts and scientists via a Hive table. So that's a SQL interface which I can use to query the data. Another example. Lots of external parties deliver their data or export their data to us on a SFTP file share. Generally, this is either a bunch of CSV files or a single zip file which contains CSV files or JSON or some other format. In this case, we copy it to the S3 bucket and again do some processing to make it available in a Hive table. Last example is we import Google Analytics data from Google BigQuery tables. In our case, we get a daily dump of Google Analytics data in a BigQuery table. We trigger an export job which dumps an Avro file onto Google Cloud Storage, which again we then copy to our data lake in S3 bucket, transform the data in some way that we like it, and make it available as a Hive table. To support all these transformations and processes, we created a library, which we named data flows. So it's a supporting Python library with a bunch of custom hooks and operators and helper functions to give us some building blocks to apply on the data. The idea is that we build reusable components since a lot of our data flows or ETL jobs are very similar, and we tried to apply a functional approach to transforming the data. So here's an example. On the right we see API into an S3 bucket. So this is a very common transformation or ETL job which we do. We have some API such as Salesforce or HubSpot or Google AdWords, and we want to load the data onto an S3 bucket. What we saw in the Airflow codebase is there's a lot of these A to B operators, and we kind of wanted to avoid having Salesforce to S3 operator, and HubSpot to S3 operator, and Google AdWords to S3 operator. We wanted to create a bit more modular building blocks and avoid the overhead of creating lots of operators. So what we did, we implemented separate hooks for each API, which we can then load or use into a single API operator. And the hooks themselves handle the specifics of dealing with the API. They handle the authentication, for example, Salesforce. You can only query it with this special SOCL dialect, and each API has their own specifics. And for various data sources, we also have, we saw lots of similar flows, just with very little differences. So for that, we implemented special file system hooks, basically for dealing with, for example, SFTP, S3, local file system, HDFS, etc. Each hook gives us basically a standard interface to talk to. So it implements basic Python file system operations such as open and glob arm3. And then with these building blocks, we have a single copy operator, and we can simply drag and drop these hooks in there. last building block we built. Once we loaded the data on the cluster, we did a lot of basically the same process. We read the data, applied a couple of transformations on the data, and then wrote it again to the process S3 bucket. The transformations that we applied were very much the same. Generally, it's anonymize the data, do some typecasting, do some mapping from column A to column B, for example. And we try to create reusable components. So we created this compose function. Basically, the only contract that it has, it should accept the data frame and output the data frame. And then with this compose function, you can string together these transformations and have a single operator in which you just dump this compose function with transformation string together. So instead of creating many operators and string those together, we have a single operator, single task, and then in there you can string together operations on your data frame. So one of the first examples, Salesforce, read from Salesforce to your unprocessed bucket, and read again, apply some transformations, anonymize the data, and then write to a process bucket, and finally make it available in a Hive table. This becomes, in our case now, a very simple and concise piece of code. We have a Salesforce query operator. You give it this special SOQL query. You give it an output path, which then writes to the S3 unprocessed bucket. And then from reading the S3 unprocessed bucket into the processed bucket is also a very concise bit of code with this PySpark operator. So it takes this argument transform callable with a single line of code to compose a couple of transformations to apply on the data. Next up is Julian. He will.
Can I ask a question?
Yes. Go ahead.
How do you deal with schemas? Schemas on,
Yeah.
On the data. I saw you mentioned a couple of times
Yeah.
transformations and recasting and
Yeah.
mapping.
We try to enforce schemas while reading. The opinions on this in data lakes and big data platforms vary a little bit.
You need to at least make sure that or check for personal data. That's
So while pulling in the data, we enforce a schema. If it doesn't match the schema, we don't put it on the data lake. And for personal identifiable information, when creating the ETL job, we select certain columns which contain personal information, and then we apply anonymization transformations on that.
Did you write your schema checking and stuff? Did you write that yourself? Or,
So we try to read the data with Spark job, and Julian may also show you some more of that. Oh, of course. Yeah. Go ahead.
Yeah, sure. So the question would be for the anonymization stuff.
Mm-hmm.
Do you do like how would you anonymize this data? Is it like hashing, or do you store a table?
Yeah, it's not okay. It's a kind of pseudo anonymization. So we apply SHA-256 with a salt, and then for a human it's unreadable.
Also, the point there is more to make it not readable for the analysts, for data scientists. So it doesn't have to be like totally secure, but at least not easily readable, let's say.
Need your watch as well.
Yeah.
Okay, so thank you, Bas. My name is, as Bas already indicated, Julian Ruiter, and I also work at GoDataDriven as a data scientist, and I've been here for a few months now. And we work together on this project. And for the remainder of the presentation, I wanted to basically describe a bit the testing procedures that we use to verify that the stuff that we implement at least more or less works. And then I'll go into some lessons that we learned during the whole process towards the end. So for our testing, one issue that we ran into while building this system is that orchestration services can be quite difficult to test because you have a lot of different external dependencies, such as APIs, file systems, and databases. And what we also had is that we had basically a lack of any realistic data sets in the testing environments which you could readily use, because most of the data that we had was all production data. So that's why for our testing strategy, we thought we'd divide it basically into a three-pronged approach, where first we comprehensively test our data flows package to make sure that the building blocks that we use actually do what we expect them to do. For functionality that is specific to one or two DAGs, we have additional tests for that, only specifically for that DAG. And then finally, to test the whole flow from end to end, we do some manual testing in the acceptance environment. So like I said, the first part is basically ensuring that what we implement in data flows, that it works. And for this, we basically use a lot of unit tests, in which, for example, for the transforms, which Bas described, we have a bunch of example data which we created, and also some expected outputs. And we can use this to verify that these individual transforms do what we expect. And for our hooks and operators, we usually do mock executions with dummy data to also check if they do what we expect. And for in some cases, we also go a bit further and to try to do some integration testing, but this is a bit more challenging because we have external dependencies, and for example, not all the APIs have demo APIs which you can talk to, and they can be quite difficult to mock extensively. And the same goes for file systems. But so for at least for the majority of the hooks that we have, we, for example, have some integration tests which test against a demo API, which is the case for HubSpot, for example. And for some file systems, we also have mock file systems in place to, well, at least check the operations there. And to automate this process, so we don't have to do it every time ourselves, we basically implemented a CI/CD system in Bitbucket pipelines, in which we use the tool PyLint to perform static checking for our code, so in terms of style, but also of correctness. We use a formatting tool called Black, which I think is recently quite a recent tool, but it basically enforces a common formatting style, which is very useful because we have multiple people working on the same project, and at least this ensures that our code always looks the same way regardless of who wrote it. And finally, we use PyTest for actually running our test suite. And we can also run, before committing our stuff, we can also run the tests locally using Docker, in which we basically have the same image that we have in our CI process as well. And one limitation of this approach at the moment is that our deployments themselves are not automated because we can't actually push stuff into the environment, which is why we actually have an Airflow DAG, which basically polls the repository every so many minutes, and then does a git pull and updates the environment and installs any new updates that it finds. For the DAGs themselves, we basically have one main test that runs on every DAG, which is the DAG integrity test. And basically what this does, it goes through all the DAG files, checks if there's a valid DAG object in there, so that it actually compiles as valid Python and produces a valid DAG. And this is quite a nice test that we adapted from a previous meetup talk called the 7 Circles of Data Testing Hell with Airflow, which was from the previous meetup. And finally, we also have them per DAG, depending on what's implemented in the DAG. We have some DAG-specific tests, which, for example, if we have a lot of transform functions in there, we test them on example data sets that we created. And if there are any DAG-specific classes of functions, these are also tested then in these DAG-specific tests. And then finally, for the acceptance environment, we basically, so the idea is that we basically have two exactly the same environments. One is UAT, and the other one is in our production environment in which the actual DAGs run. And basically, we first develop stuff on a feature branch, which then, when it gets pushed to the development branch, we check whether everything still works in UAT. So here we actually run the DAGs and see if they do what we expected them to do. And then, only then, if they pass this, it's promoted into the production environment via the master branch. And basically this testing, the acceptance environment is a lot of manual testing, unfortunately, where we check out the feature branch, we update the environment, and we trigger the DAG execution to see if it does what we expect it does. And one important thing here is that we don't want to use any personally identifiable data in our test environments, also because the security doesn't like this. So, but we do want to have data sets that reflect the data, the true data structure, because we want to know if it actually works or not. So what we do is basically we, for the data sets that we pull in, we dumbify any personally identifiable fields on the fly, which then gives us more or less true input data without exposing any personal details. And for this we use a combination of different approaches, but one important part is this Python library called Faker, which I think is quite nice, which basically for different locales allows you to very quickly generate a bunch of fake data, which more or less represents the structure that you would expect it to. So you have more or less data that looks real, but is at least not personal. So some important things that we learned during this this whole endeavor is, so one thing that we noticed in a lot of the DAGs is that people, it's important to realize that when you're implementing a DAG in Airflow, that's basically a configuration file, so it should also be treated as such. So you shouldn't be doing any computation or fetching of connections or stuff in your DAG, because that basically means that every time Airflow runs through your DAG to see if your DAG's been updated or not, it will be doing all these calculations. And one thing, for example, that we saw is that a lot of things in older DAGs that we got, that connections were fetched, for example. That means every time Airflow hits this file, it will be fetching this connection from a database, which from a performance view is a bad thing, of course. And it's basically because Airflow keeps running over your files. And another drawback is that you can also not test your DAG locally, because you might not have this Airflow database with all these connections locally as well. And so basically what you should do is we basically use two different approaches. Either we move these operations elsewhere, so we move it into a hook or an operator, so that stuff is only done when an operator actually executes. Or if you really need to, for example, fetch a connection in your DAG for whatever reason, at least make sure that it happens lazily, so you don't actually fetch a connection until the details are actually needed, which happens in one or two other DAGs. Another thing is a bit where what Bas talked about earlier is, I think, one thing that we try to enforce in our data flows code is to at least have clear, well-defined interfaces for example, the API hooks, for the transforms, or for our file system hooks, so that we can easily, so we could create a bunch of components which we can then easily switch out for one another. And this allows us for the file system hooks, for example, to extract over files, different file systems, for the API hooks to abstract away details from the APIs, and for the transforms to basically create a bunch of generic transforms that we can easily hook together. And this avoids having to implement many very specific operators, which we saw in some other code and some other projects, and basically allows us to have a few very generic building blocks which can be used to build more complex behavior. And just to give one example, for example, with the file system hooks, we can, with this bit of code, we can use the file system hook, sorry, the S3 hook, to open a file on S3 and then read whatever from it. And but with exactly the same code, but just switching out these two hooks, we can also read the same from the HDFS file system. And the nice thing about this is, because they have exactly the same interface, you can also build more generic stuff like the copy file operator, which Bas alluded to earlier. In this case, it becomes very easy to copy files using this copy file operator from different file systems by simply changing the two hooks from which we copy, in this case the source hook and the destination hook. So in this case we have an HDFS hook to copy from HDFS and S3 to write to S3, but by just plugging in different hooks here, we can use it for any combination of file systems, which I think is quite nice, instead of having a copy HDFS to S3 operator and stuff like that. And so a final point that we tested is one thing that we found out when we were implementing many of our DAGs is that while we started out with basically one single DAG file, which is quite manageable, at some point we also have like template files for our SQL statements. We have Spark schemas which we store as JSON. We had different config files, so it became a bit unmanageable if we kept all these files in top-level directories within our project. So and what happened was that DAGs were deleted, but the templates were left behind. We had shared configurations, which led to implicit dependencies, and basically this became a bit of a hell to maintain over time. So that's why what we switched to recently, at least, is to have like a single directory per DAG as our main structure for each DAG. And then basically this directory contains, for example, in this case, a configuration file for the DAG, which contains some basic configuration options. The DAG file itself, which basically contains the Airflow DAG code. And in this case, a directory containing our Spark schemas, our SQL templates, and also in this case, some of the DAG-specific unit tests that we have. And I think an advantage of this is that we have basically all the dependencies in one place. We have no cross-DAG dependencies because all these files are in this DAG directory and other DAGs are can't access it. And this makes it much easier for us to add new DAGs, to modify existing DAGs, and to delete old DAGs as well without worrying about breaking stuff elsewhere, which I think is quite nice. And so finally, just to touch on some future work, stuff that we're still working on. So one thing that I'm still busy with is trying to see if we can contribute some of these hooks and operators back into the Airflow project, because well, I think it's great that Airflow is open source, and I think if we use it, it's one of our obligations to see if we can help improve the current state of the art as well. And I think in this case, the file system hooks would definitely simplify the current code base, because the hooks that are in there at the moment have a lot of different interfaces and therefore is not as reusable as the ones that we implemented, I think. But an issue with this is, of course, that if we change interfaces, that backwards compatibility might break other people's projects. So that's something that we're still working on together with the Airflow contributors. Something that we would really like to do is to have better integration testing of our DAGs. So basically we can run our DAGs from start to end and test their execution automatically in our CI/CD system, instead of because at the moment we're limited to testing their integrity and basically the different transform functions that we add into the DAGs. So this is something that we're still working on, and something so a bit outside of Airflow but more related to this project is that we're also interested in seeing if we can use other tools from AWS, such as SageMaker and Athena, to step away from the EMR setup that we're using now, because that keeps the cluster up all the time, and basically move to a much more scalable serverless system using Athena and SageMaker, for those of you who know what those are. But that's more future work. And with that, I think we're happy to take any questions.
Yes. So thank you, Julian and Bas.
There's a question in the back, I think.
Are there any questions?
I got a question about the DAG layout. So what happens if you have like a template that is still used by multiple DAGs? Do you still have like a top level templates folder for those? Or do you just copy them over to the second DAG folder? Or?
So at least up to now, we haven't had that case yet, I think. But I think in the end it's a bit of a trade-off between having dependencies between the DAGs or not. So in this case, if you have a template which is shared between 2 or 3 DAGs, and you're working on one of the DAGs and then you change this DAG, this template, you might not realize that you're also changing the behavior of the other DAGs. So that's something that you would need to keep in mind if you have shared templates. And I think in that case, I would personally be more for copying it, because it makes it more reliable in the long run. Than sharing too much between DAGs. But it's a bit of a trade-off between duplication and consistency, I think.
Question about security authentication. How do you store your authentication details against databases and so on? Are these encrypted or just stored in the file system?
So for the connections themselves to the APIs and stuff like that, we basically store everything using Airflow's infrastructure for storing connections. So that would be then encrypted in the database that Airflow uses. In terms of like securing the environment, we have everything runs in AWS, and we have a Bastion host which we can connect to and use that to connect into the VPC, so to say. And basically the masked buckets, so without personally identifiable information, they're accessible by any of the instances within the VPC. And the unmasked buckets, which contain more personal information, they need special credentials to be accessed. So that's how we make a difference between like the more sensitive data and not. What we originally used in the system was mostly snapshot based. So they took a full snapshot of the state of the system at that point. But the problem with that is that it becomes very big very quickly. So now basically what we're doing is for most of the sources we try to query what's change between basically the previous DAG execution and our current DAG execution, and only store store those differences. And then in derived tables, then you need to take the newest version of the record essentially, and stuff like that. So that's how we build our history without trying to duplicate everything every time.
You mentioned using Hive to expose the actual to the business analyst or data scientist. How big is this data we're talking about? Like how big is the actual, say, if I wanted to select from and get everything that's on there? Is it like very big, or did you use Hive to future scalability?
Do you know, Bas, the exact?
Yeah, it depends a bit on the data source. Great. Yeah, it depends a bit on the data source. Some are very small, so in the number of a couple of 100 megabytes. I think the largest one goes into tens of gigabytes.
Yeah, so in that case, I've seen Athena. The Athena can be the replacement of what you do in Hive.
Yeah, that's what we're aiming for. So we are currently in the process of moving away from Hive with U on top as a SQL interface. The current state is that we've done some testing with Athena. For us, it was very positive, and we try to move there.
Also, a little question. While doing the unit test, do you mock all the objects, all the file hooks, no matter which is the environment, like S3 hooks, Spark hooks, everything? Do you mock everything? Like, is it a perfect mock of every object?
Yeah, that's what we aim for. We try to mock everything, indeed. Yeah, correct.
But some of it is more. So for some file systems, it can be quite straightforward to mock them. For example, S3, you have Moto, which is a mocked Moto. But for others, it can be a bit more challenging, and it depends a bit on how far you want to go. So some of the unit tests are more like white box testing. So we verify that they call what we expect on the underlying libraries, which is the easy and lazy approach. But yeah, to really mock everything becomes a bit too extensive at some point, which is, yeah.
That's why I asked you that, like, yeah, if you are doing, maybe it's too nice if you can share in the meetup or somewhere else, and it would be really handy for your company policy differently.
Yeah. For example, the file system stuff, we tested it. So most of the tests hit either local file system or Moto, for example, because that's easy to mock. And then the others, we, at least for the general functionality, we assume that it's covered by the other tests, more or less. And then for the file system specific stuff, we basically verify that we call the correct method, and some manual testing in there, of course, as well. But otherwise, you end up with also with like a Docker image in which you have to have your some kind of S3 file system, some SFTP, some FTP, and that becomes a bit complicated very quickly. Spark as well. So yeah.
Question over there.
Yeah, thank you for your talk. I was wondering about, so as I understand it, you're testing the operators or hooks, right, per DAG. And yeah, we're mostly interested in like the validation test of after running, for example, a transform step. And did you mention that that's something you're still going to do? Did you look further into that? Like, if there's like a nice way to modularize that, or like, what's your experience with that?
So at least for the transformations that we do in Spark, we so basically we have the PySpark hook, which reads data using Spark and writes it in the end back using Spark as well. And then in between we have this transform callable, which Bas showed. And that's basically then a bunch of functions which are composed into a single function, then which basically build up the whole transformation plan in Spark. And because that's basically one function, we can take that out, run an example data set through it, and see if it does what we expect. And then in data flows, we have tests to verify that the PySpark operator does what we expect. So that's how we have like these DAG-specific tests to test the transforms themselves, and then the data flows unit tests which verify that the operator should be doing what we expect it does.
Yeah. To add to that, the interface that we use is basically data frame in, data frame out. and allows us to create simple unit tests. And we can also create sort of integration tests because we can chain all these transformations together.
Cool. So one more question by the guy in front here, and then we will go to the break.
You mentioned that you keep the EMR cluster running. That's, I think, the EMR cluster for the data science lab, not for the ETL jobs.
We use it for both. So we do scale it up and down during working hours and outside working hours. And it scales automatically, but yeah, the problem that we have there, and the reason why we want to use Athena, is the auto-scaling is very slow. So you can only specify the auto-scaling rules in blocks of 5 minutes. And then, yeah, it takes like 10, 15 minutes to spin up another machine.
SageMaker is indeed interesting, but isn't it also like disadvantages both in a vendor lock-in and the fact that you don't have any spot pricing currently in SageMaker?
That is very true. Yeah, the vendor lock-in on AWS is for us, for this project, not an issue. Yeah, the spot pricing, you could do it on the task nodes of EMR, but yeah, for the core nodes and the master nodes, you cannot use it.
Cool. So thank you for your questions. If you have any more questions, I think Julian and Bas will be around. So let's now go to the break. So let's have a 10-minute break, and then we will continue with Tahir. Thank you.